In this video, we're going to work through an exam-style problem on matrix algebra that sort of takes everything that we've learned so far and puts it all into one question. So do pause the video and try this for yourself first. Okay, so we've got this matrix B, and it says, given that E equals 2, 2 minus 1 as an eigenvector of V, find P and Q and find the eigenvalue of B corresponding to E. All right, so let's try this. So if 2, 2 minus 1 is an eigenvector of B, then we know that when we apply B to it, to 2, 2 minus 1, we should get lambda times that. So that should be 2 lambda, and minus lambda. Well, we can use that first row to find lambda by saying it's 4 times 2 plus 1 times 2 minus 2 times 1 should equal 2 lambda. So we've got 8 equals 2 lambda and lambda equals 4. And now we can use the second row to find P. So 1 times 2 plus 2p plus 0 equals 2 lambda, which is 8. So P is 3. And then we can use that third row to find Q. So minus 1 times 2 plus 1 times 2 and then Q times minus 1. So minus Q is minus lambda. So that's going to give us Q is 4. So now that we know that, we want to find the eigenvalue of B corresponding to E. Well, we've already found that. That was lambda. That was 4. Okay, so we're done with part A. Part B, show that B only has one real eigenvalue. Now, we know that the eigenvalue found so far is 4. So we need to show that's the only one. So we're going to consider the determinant of this. So we're subtracting lambda times the identity from it. We found that P was 3, so that's going to be 3 minus lambda, 0, minus 1, 1, and what was Q? Q was 4, so 4 minus lambda. And we're hoping to show that there's only one solution to this. So let's explore that characteristic equation. So that's 4 minus lambda times the determinant here, which is this times this minus 0. So that's 3 minus lambda times 4 minus lambda. Then minus 1 times the determinant of this, which is 1 times 4 minus lambda minus 0. So that's nice and easy. And then finally, it's plus 2 times 1 minus this. So that's 1 and then plus 3 minus lambda. Well, this is going to be easy to solve because we've got 4 minus lambda as factors throughout. So do we get anything nice here? Maybe not. So let's see. So pulling out a 4 minus lambda, what am I left with? I'm left with 3 minus lambda, 4 minus lambda. Expanded is lambda squared minus 7 lambda plus 12. And then minus 1, because it's one lot of it here. And then it's plus 2. So neatened up, that's 4 minus lambda, lambda squared, minus 7 lambda, and then we get plus 13. And what we're trying to show is that lambda equals 4 is the only real eigenvalue. And it is, because lambda squared minus 7 lambda plus 13 has no real solutions. So, and we can show that with the discriminant. And our proof there is that b squared, so minus 7 squared minus 4 times 1 times 13 is 49 minus 52, which is minus 3. So yeah, that's giving us no solutions, so lambda equals 4 is the only eigenvalue. Okay, on to part C. Determine the eigenvalue and eigenvector of A, which is B plus B squared. So this is where the matrix algebra kicks in. B has a single eigenvector, which is 2, 2 minus 1, with an eigenvalue, which we already found was 4. So any sort of combination of it like this is going to have the same eigenvector, but its eigenvalue will be different. And how do we figure this out? Well, The answer is going to be that the eigenvector of A is 2, 2, minus 1, and the value of lambda is simply our old value of lambda, 4 plus 3 times 4 squared, and so we've got 3 times 16 is 48, plus 4 is 52. And yeah, the justification for that is you can apply b multiple times and times it by stuff and add b again to this vector, and all you're doing is stretching it in different ways. By how much have you stretched it? Well, it's by a factor of 52. So relatively easy once you know eigenvalues and eigenvectors of a matrix to find new eigenvalues in the same eigenvector of any sort of combination of them, like this. Okay, so that's all for now. I'll see you in the next video.